So this is basically, as you can see, an implementation of the assignment that you have been provided with. In particular, here you can see you have basically a dispenser in red. This is a conical structure. You can think about it as an upper stage, okay, of a launcher. And on top of it, you have, in this case, a multi-payload. This is a multi-payload adapter, so you have two payloads. In particular, you have two satellites that have to be released, okay? And the concept of this is that you have to, let's say, provide the adapter, so the red part, with a spinning motion. In particular, you will have to provide, for example, two counter-rotating forces. You can provide a torque, whatever, so that the two satellites will disengage, okay, and will be put on orbit. In particular, the additional elements that you will have to think and you will have to provide are the release mechanism, okay, that will connect the two payloads, the two satellites, to the payload adapter until a particular value of the spinning force or timing, this is up to you to model, is reached, so that this release mechanism will open up, and then eventually a force, which can be modeled, for example, as a spring, will eventually act on the two satellites, releasing them. Okay, so basically, you will have something like this. This is a simulation I performed. Okay, you see, it rotates, and then at a certain point, you see the releasing mechanism opens up, and the two satellites start being, deployed. Okay. What you can see here in these graphs, okay, you can. I mean, it's up to you to choose which variables you want to show. In this case, for example, here you can see on top right the angular velocity of the payload adapter. Of course, it starts from 0 because initially the angular velocity is 0, and then it basically reaches a constant value after let's say transient, which is the spin motion that you provide. Okay, in this case, for example, I provided two thrust forces on left and right. So these are two forces which I applied. You can think of it as two thruster, okay, which are attached to the payload adapter, which provide this rotating motion. Okay, again, this is a way to model it. This is the closest to reality, but you can also provide a torque directly instead of two, opposite forces. Then you have a tie down, meaning, again, you can think about it as a bushing, something of this sort that you have already seen with Catellani. In this case, actually, before passing to this, the thrust, for example, this one, you can think about it as something of this sort. It's a little bit stuck. Let's see if it actually is able to go on. So what I'm saying is that the thrust should be thought of as a force. There you go. As a force which starts from 0, then smoothly goes up to a maximum. It maintains this maximum value, and then it is shot down, because when you have a thrust, it's not going in a limited way. Even for fuel consumption reason, you basically have impulses. Okay, you have short time force application, okay, and then it shut down. Okay, so this is what you have to foresee, something of this, like this, something that at a certain point basically acts no more. It is just shut down. And the saying goes, for the tie down, okay, in this case I use the general force that basically holds together the two satellites to the payload adapter. Okay, and again here you can introduce a rigidity, a stiffness. You can introduce a certain value of the damping, and a certain time. For example, this is 0.1. Okay, where this mechanism disengages. Okay, so you have to basically tune the effect of the thruster, which puts into into rotation the payload adapter. You have to tune the effect of the release mechanism that has to open up, and of the spring force that eventually is released and allows the separation of the two satellites from the payload adapter, from the dispenser. Okay, so this is what you have to do, and the goal is to do so in compliance with the requirement that I have prescribed you with, meaning that the release phase must not last more than 10 seconds. There has to be a minimum distance that has to be maintained between the center of mass of the two satellites, because they have to not collide eventually. You have to minimize the spin of the two satellites, and so in so doing you will have to produce a certain amount of post-processing results. In this case, as I said, I have for example, the velocity, the angular velocity of the payload. You can also, if you want, portray the distance between the center of masses of the two payloads, of the two satellites. You can portray, for example, the value of the angle, not only the velocity. Okay, so this is up to you a little bit, okay, to show what you did, to show that you have accomplished the requirements. You will be assigned different values of this design variable. Okay, so in this case, the mass of the two satellites is 400 kilos. Okay, but with this design variable, I can basically modify the inertial properties of the two payloads. What do I mean is that in this case, for example, you have that the standard value of this design variable is 0.1. So if you go back and check the mass properties of the payload, for example, the left one, you see here the mass is basically 400 kilograms times the variable. So the variable in this case is 0.1, meaning that now the mass of the satellite is 40 kilograms. Okay, each group will be assigned a different value of this design, so that eventually you will have slightly different cases. Okay, and the idea is that today you have to provide me with the names of the groups. Okay, so that I can assign to you a variable number. Okay, and then you can move on with your assignment. The result of the assignment will be the model, so only the command file, and the report. Okay, you can do it as a PDF, you can do it as a PPT, Word, whatever. Okay. Any kind of question, any kind of help that you will be needing, you can email to Daniele Catelani directly. Okay, you already have the email. Okay. Yes. There was one thing I wanted to show. Oh yes. Okay. So let's pin down the groups. So So first group is, for example, La Bella, then and then okay, same group. Okay. Then there was another group. Giattanasio, I think. And then Stentella. No, Stentella. Let me check the emails. Okay. Gianattasio, ho sbagliato. Ok, no, non lo trovo. Mi pare fosse Stentella. Ok. Ah, no, Gianesini. Stentella. Okay. You're in the group with people you don't know. Okay. Okay. I was expecting two more groups, in fact, because when we were attending the seminar, there were 15 people. So I don't know what about the others. This is going to be a problem. Okay. So we can assign a design variable as such. Now it's 0.1, so we could go, let's say, 0.1 for La Bella, Soddisfattoria, and Sena. Okay. Then we can go 0.5 for Pirolo and the others. And then we can go to 1. Mandala, Genesini, Stentella. Okay. So this is the value of the design variable. Okay. Okay. Additional questions? Again, you are not constrained to any kind of methodology you want to use to model, these three elements that you have to introduce in the model. You can use, a constraint, you can use a bushing, you can use generalized force, you can use whatever, as long as the requirements are met. Okay. And of course, you can use, again, the command file that I gave you, setting this value of the design variable. Okay, you can do it yourself. Okay, you can go here, because eventually, in that model that you've been prescribed with, you only have this. Of all these elements here, you have nothing, no? Of all of this. You only have this, and you have to set it here, that value. Yes, sure. Okay, you have nothing of this. This is eventually what you should be modeling, okay? Again, this is just an example. What you will have instead is this. Okay, this you will have, and it's this one. When you click on it, you will have this. Here you should set the values that we have agreed. this will automatically modify the mass and so the inertial properties of the payloads. Okay, so this is it. If there are no additional questions, we can move on and go on with the exercise. Okay. All right. So I will stop from here. Okay, and we'll share it from here. Just a second. There you go. Okay. Okay. We'll start with this. This eventually I can close. Okay. All right. So the idea now is to basically conclude the section with an exercise as usual. And then eventually they're going to be the last chapter. Okay, the last chapter of the course, which will end next Friday. We'll deal with the different techniques, basically two, Gaussian iron method and dynamic method of condensation. Okay, so how to reduce further the number of degrees of freedom of a model when you can trade the approximation, so the degree of accuracy of your model with the number of elements and number of nodes, so that you can have a faster simulation, a faster model, a lighter model, a little bit less accurate, but on those things that maybe you don't care. So the cost, is affordable. Today and tomorrow, we'll instead close the present chapter on the use of finite element on multi-body analysis with an exercise, as I was saying. So we have an example. In particular, we're going to have a 2D element at our hand. At the very last part of the previous chapter, we were able to say that the position of a point of an element within the element J in the 2D case could be written as R dot R without dot, of course, plus AI operated over R over Ij, okay? And in particular, from this, we elaborated that P dot Ij, so the velocity, was R dot I plus A theta I applied over R Ij applied over theta dot I plus A I n Ij B2 I QF I dot. Okay? Using this expression of the velocity, we could eventually come up with a mass matrix deriving from the following integral over the volume of the body, the density, and then we had the following matrix. We had identity matrix, we had A theta I R over bar ij, and then we had A I Nij B2 I, the V. Then we had Rij transpose over Rij. And then we had Rij applied over A theta transposed over A I over N Ij MBR 2. And then eventually at B2I transpose apply over N I J transpose apply over N applied over B2. Okay, and here everything is symmetric. Okay. So this is basically the, if you want, specification of what we have seen in the 3D case and the 2D case that we will going to see now. Okay. You know that, of course, this product of two matrices A theta and A basically give us a particular matrix. It's a 2 by 2 matrix that we can define like such. So we can write that A theta I transpose over A is the matrix I tilde, which is very simple. It's 0, minus 1, 1, 0. You can verify it by yourself because A is the typical cosinus minus sinus, sinus, cosinus. This is the derivative with respect to theta. If you do the transpose over A, you get this. So very easy. Okay. We also want to introduce the following inertia. S I J C, which is the integral over Vij of rho Ij n. And this, for what we have seen as the definition for n, is C2 Okay, this is by definition. So these are the inertia shape integrals that we will need for the 2D case, which are of course simpler than those of the 3D case. Then we have S I J C C, which can be thought of as B1 Ij transposed Cij transposed the integral over Vij on rho ij. And it's nothing than Cij transposed, applied over the above matrix I tilde, so this one, and Cij. Okay. And then we have SCF, which is B1 ij, C1 ij transposed, both. And then we have again the integral over the volume of the density. And here we have Psi ij transposed, apply over Psi ij. Okay. Okay. Now, with this in mind, you can move forward to the exercise. Okay, so these were just some definition. These are all definition. Okay. Let me should work like here. Okay. Okay. So if we have written, let's introduce our case. So here you have an element. Okay. You see, our case is our element. It's basically in the 2D case, it's a beam element. And you see that you have two nodes. You have two nodes. This is the first node. This is the second node. Then you have the axis of the element, I1, I2. Then you have the intermediate floating frame, the intermediate frame, which is this one here, and this one here, which is parallel to the element frame, but located in the origin of the body frame, okay? B2, B1, okay? So this is the origin of the body frame. This is the intermediate frame, which is initially parallel to the element frame, okay? The intermediate frame forms an angle beta, ij, which is constant because we know that eventually these two frames are parallel, but then these will deform, it will move, and these instead will retain its orientation constant with respect to the body frame. And then the body frame has the typical angle theta with respect to the inertial frame. This is the theta that is inside the rotation matrix that we know. Okay. And last information, we have a series of nodal coordinates. You see, we have E2, E1, E3, E4, E5, and E6, which are the displacement in the horizontal and vertical direction and the slope, okay, at point 1 and point 2, okay, and node 1 and node 2. 1 and 2. And you see they have an overhead because they are expressed with respect to the intermediate frame, which has an overhead. So just to be clear, here you have an overhead, I2, and here you have an overhead. Okay, meaning that this quantity is expressed with respect to I2, okay? Okay, so it retains basically this constant term, okay? All right, why do I say that? Because we know that so we have the following: x over bar ij c ij over e ij. Okay, so we know that the position within the element of a point within the area, described with respect to the intermediate frame, can be expressed again resorting to the values of the nodal quantities expressed with respect to the intermediate frame, making use of shape functions which are always the same. Okay, they do not have to be adapted. Okay, so this we know already is the very well-known thing written like so. Three c squared plus 2c to the cube, the third, then we have 0, and then we have L c minus 2c squared plus c to the third, and here we have 0. Here we have c, 0. Then we have 3c to the second minus 2c to the third, and here we have 0. And then eventually we have L multiplying c to the third minus c to the second. All of this, please make sure to note that all of these have an ij on top. You see, because here you have an ij. Why? Because eventually this ij is a shortcut to basically avoid putting these two subscripts on the xc. Why? Because eventually L, this L should be Lij because it's the length of the element j. Okay, and also xc is the normalized distance with respect to the length of the element j. Okay, instead of putting j all over the various quantities, I just put it here on the matrix. Okay, but this is the meaning. But as you can see, it's always the typical shape function, which is always again the same because it depends on the physics, and we always made use of the typical Euler beam 1D model. Okay, now we have also that Rj over bar could be written, if you recall, as C2ij x ij. And therefore, this could be written as C2ij C ij E overhead ij. What is this C2ij? Well, C2ij, you can already anticipate it, is the rotation in the 2D. So, knowing that the angle is beta between the intermediate frame and the body frame, you will have to write it like such. Minus sinus of beta ij, sinus of beta ij, and cosinus of beta ij. Okay, it's the typical 2D matrix. There's no. Why is it so? Because here we are going from the element to the body frame. So we are going from the local to the less local, okay, which is the body. We are going from a very specific frame, we're going back, okay? So we are, in order to express the coordinates from the intermediate frame to the element frame, to the body frame, you have to rotate the vector, okay? So that's why you have this rotation matrix. Why am I saying that? Because now we also introduce another relationship, which is the following. Okay, we can actually stay like this. I think it's a little bit easier. So we also have this. We also have that Eij can be written as C1ij times QEij. So this is again the relationship which relates the nodal coordinate expressed with respect to the body frame to the nodal coordinate expressed in the element frame, in the intermediate frame part. This is where the definition of the matrix is C1 and C2, if you remember. Okay, but in this case, so this is a 6 times 1 vector. This is a 6 times 6. This is a 6 times 1 vector. Okay, while the other one was a 2 by 2 because we were in the two-dimensional space. Okay, so if you want, I can put it, extensively. So this is a 2 times 1 is a 2 times 2 because this is a 2 times 1. Okay, so it's a little bit more, a little bit bigger. And so we have that C1ij can be written as such. Let's see. And then I'll ask you why, in your opinion, it's written like such, like so. You have let's write it a little bit more in a clearer way. Now, I wanted you to notice this. You see, here you have cosinus, sinus, minus sinus, and then you have cosinus. Okay. While in this case, the previous one, you had cosinus minus sinus, sinus, cosinus. So this one, the sign of the sinus are opposite. Why is that? This is always a rotation matrix eventually, no? To connect the intermediate frame and the body frame. But why the sign are opposite? Can you guess? What is the intuitive reason that comes to your mind? Why is the cosinus are the same and the sinus are opposite? Okay, the rotation is opposite. So this is in fact the reason, but why is it opposite? Can you guess? No, the bit angle, you can basically, from an absolute point of view, it's always the same angle. What changes is how you rotate something. So why are you actually rotating on two different directions? Because, you see, here in C2, I am rotating something which lives in the space of the element frames, okay, in the intermediate element frame, to get it to the body frame. Okay? Instead here, I'm rotating something that lives in the body frame to get it back to the element frame. So it's the opposite. Is this clear? That's why you have here the opposite signs in the angle. The angle is the same, but it's opposite in terms of angle. Okay, in case you wonder. Now, without any loss of generality, we are simplifying hypothesis. We only consider one element, okay, a single body, a single element body. A one element body. This has two consequences. The connectivity matrix is the identity matrix. There is nothing to connect. Okay. Actually, both the identity matrix is a matrix of ones, which is different. Okay, if you want. Okay, so I don't know if how you want to call it. It's a matrix basically made out of all ones in all elements. Okay, I don't know if how you want to call it. If you want, I can represent it like this. Okay, meaning that eventually it will not appear in our formulation because again there is nothing to connect. It's only one element for the body. The second is that when you express the element like this, the element coordinates, we typically did it with a reference coordinate plus b applied over fi, where this b, sorry, 2, was the reference matrix, the matrix enforcing the reference conditions to basically to block, if you want, the body frame, if you remember. This was enforced, for example, to establish the boundary condition between one body and the other, if you remember, the slider mechanism in which you have the bending of the beam, and you had to establish how the body frame would follow the body. Okay, this was made out of that. If you only have one element, again, this concept vanishes. Okay, because you only have one element, so it's not appearing. Okay. All right. And therefore, the consequence of all of this is that our R, ij, the position, is always, again, n applied over QE, and n is C2, C1. Okay? So you see there is no B1 in here. Okay? You don't have it. You should, but you don't, because we are in a simpler case. Okay. Very well. Now, with all of this being said, we want to first calculate the mass matrix. Element. So we know that the position, again, is Pij I plus A I n Ij QE. So let's calculate this I first. Well, we have said it, no? If you remember, A is always the matrix of the rotational, the rigid rotation, so it will be expressed in terms of the theta. Okay, so again, here there is no surprise. And so here we have A of theta I minus sinus of theta I. Okay. Very well. Now we have to again proceed with the velocity vector that we have in fact already defined before. So this is our I dot, and that's fine. Then we have A dot. And Ij QEI plus A n QEI dot. And then we know that this can be written typically, we have already said that, as such. In this case, theta dot is a scalar quantity, no? Because it's only basically it's only one angle. Okay. What is this? Sorry, a dot here. No, sorry, minus 3. A theta. Okay, so chain rule. To derive it with respect to the total derivative is the partial derivative, and then eventually the derivative on the variable. With great surprise, this will be minus sinus of theta minus cosinus of theta I cosinus of theta minus sinus of theta. Okay. Therefore, our P dot Ij can be written as I, identity matrix, we have minus A theta Just a second. No, there is no minus here. There is a typo in the notes. Nij qei j a I and ij applied over what? The vector of the coordinates. So you have r I dot. You have theta dot I. I can write it as a vector, but we know that this is a scalar. Okay, it's a vector of one component. And then you have q e I j dot. Okay. And again, so this is something that we have already learned to do so many times. The kinetic energy is rho ij p ij dot transpose applied over p ij del dij. And again, this is 1 over 2 of what? Of q e dot ij transpose apply over m ij apply over q e ij dot, where m is the typical mass matrix that we know. And therefore, from the definition that we have here, so from here, and then from here in here, our mass matrix is the identity matrix. It's A theta I applied over R over bar ij. It's A applied over N ij. It's R ij applied over itself. It's R ij applied over I with a tilde. Well, this is the matrix that we have introduced already, no? The 0, 1, minus 1, 0, and ij, and then eventually n ij transpose over n. Okay. If you want, you can prolong this, but okay. This is the mathematics, and this is what we are going to estimate. This, just to be clear, is what comes from A theta applied over A. Okay. All right. Please take your time. So now we are going to estimate the various submatrices, okay, as we have learned to do. For the single element. Then eventually you should assemble them, summing for each element, as we have seen. And then you get the overall mass matrix of the body. And then you can build all the dynamics of the body. Okay. All right. So again, I will not repeat it, but okay, this is RR, R theta, RF, M theta theta, and so on. Okay, so if you want, I can rewrite it. So we can cast M ij as with all the submatrices MRR, ij, MR theta, ij, okay, so these are the quantities that we have defined before. So let's start it. This we have already learned how to write it. Then the integral of the density times the first matrix on the left top corner, no, of the previous matrix, which is the identity matrix. And this is a constant matrix. Where this is the mass of the element. And that's it. This is very easy. Okay, and it's constant. Okay. Now, let's move to the other matrix, which is constant. We know it's constant. This one, no? We know already. I will not move like this as we usually do because this will serve me later on. Okay, we will save time doing this before. This, from the previous matrix, results to be rho, the integral of rho, times n ij applied over n ij. No? If you look at previous, it's this one. Oh, here I lost an ij. Okay. But we know everything of this n. We already estimated it, no? For the 2D case. This, in fact, can be written as C1 ij Cij transposed over Psi ij in the Vij. Okay, I'm just bringing out of the n the terms which do not depend on space. Okay. You know, you should notice one thing here. Inside n, we should also have C2, if you remember. We have seen it if you go and check your notes. There should be n is C1, is C2 applied over Psi, applied over C1. Where did C2 go in here? C2 transposed over C2 is the identity matrix, because C2 is the rotation matrix, if you remember, no? This is C2. If you go and check. We estimated it at the very beginning. This is C2. You remember when we said that beta has two different orientations and blah, blah, blah. So if you, this is a rotation matrix, exactly, it's a 2 by 2. If you apply this to the C2 transpose, you get identity matrix because this is an orthogonal matrix. We know that rotation matrices are orthogonal. That's why CT applied over CT transposed, it's identity matrix, and you don't get it inside the expression. Okay. So all of this to say that in here, you should get a C2 transpose applied over C2, which is the identity matrix. Okay. Okay. We have defined S C C F F ij, if you remember at the beginning of the lecture, exactly as for the 2D case, C1 T transposed pi over V ij over rho ij of psi ij transposed over psi ij. Okay, so it's exactly that. So my M F F ij is exactly the first inertia shape integral. No? You can also calculate it if you want, because here we have everything, no? We have C1, we have defined, it's the 6 times 6 matrix. This is, if you remember, for the element, is in this case a 2 times 6, because it's 6 coordinates, and 2 because we are in the 2D space. Here it's transposed, so we're going to have a 2 times 6. And this is a 6 times 6. So eventually you're going to get a 6 times 6. Okay? Which makes sense because this is the mass matrix associated to the deformation. And the deformation occurs on all over the 3 nodal coordinates, which are 6. Okay? You will find this expression in the notes. It adds nothing, but just, this you have it, because we have defined the previous part. This we have stated it, so you have everything, you do the integral, and you get it. Okay. Very nice. Then, let's start with the third, which is M R theta I. So what I'm saying here, again, with this exercise, is letting you see how your code works. You calculate all of these quantities, and then you get your mass matrix. We will get also the stiffness, and then you have the mass, you have the stiffness, you can implement your equations, and then your solver will solve it for you, luckily. Okay. Okay. This, if you go and check, was rho ij a theta I applied over R over ij from the mass matrix that we defined. This you can put this out of the integral sign because it does not depend on space. So you get okay. Okay, so we can still elaborate because we know what R is. We know that R, if you remember, at the very beginning of this lecture, we said that this is N times QE. You remember, no? And N, again, if you remember, was C2, Ij, C, Ij, C1, Ij. So if we substitute everything, this becomes A theta, I, which is applied over what? C2, Ij, the integral of the density Ij and Psi, because this is eventually the only term at the end of the game that depends on phase, the element shape functions. And then you multiply it by C1, then you put it outside of the integral sign. Okay, and all of this here, the one on the integral within round brackets, is by definition something that we have already defined, which is S Cij. Okay, so all of this. Once you integrate it, what is inside the square brackets is constant. Okay, so that's why it's an inertia shape integral, because it's constant. Okay. Here you have a dependence on the theta. Here you have a dependence on time. But this is just a constant. This is just a coefficient. That's why, again, we come back to the logic of inertia shape integrals, quantities that you integrate once and then you forget about it. Because if you want to update the value of the submatrix with the passing of time, with different values of the rotational coordinate, in this case theta, you do not have to do anything. You just put your values of time and theta inside here, and you directly get your submatrix once, and that's it. Okay. And these, again, quantities like here is as we have defined at the beginning of the lecture. Okay, so this is the second inertia shape integral. The same goes for another quantity, which is MRF Ij. If you go and check, you get that this is the integral over the volume of the density of the matrix of rotation and of n. But this we have already seen. This integral here we have just seen. Huh? This is just I. Well, let's put it just like we have seen it. So C Ij, then there is the integral Vij of rho Ij C Ij C1 ij. Okay, but this is exactly what you have just seen, the quantity. So this is AI S C ij. That's it. If you go and check again, previously we had a dependence on the rotation and on time, so on the deformation in particular here. Here we only have a dependence on the rotation, okay, for this particular submatrix. Okay. Then we have the last one, no, the last two, but these are quite easy. So we have the fifth, which we call m theta theta, which in this case is what? Did I write it correctly in your opinion, this one? As a matrix? No. Why? We have seen how many variables of rotation do we have. It's just one angle because we are in the 2D space. So this is going to be, it's going to be scalar. Okay. So rho ij now, and this is why I actually reverted the order which we typically use. This one here, the integral here, we have already seen it. If you go and check number 2, here, look at this, it's here. Okay, because here it's n transpose over n. Okay, now n transpose over n, do not forget. Here, this one, you can write it exactly like this. No? Because remember that this is n ij applied over qi j. Okay? So this is exactly what MFF. Okay? That's why I did it at the beginning. Dimensionally, what do I get? Here I get, you remember, this was a 6 times 6. Here I have a 1 times 6. This is a 6 times 1. And I get a scalar eventually, you see? So everything seems to be fine. In fact, just as a final remark, if you express this QE, ij as a term 0 before the deformation, okay, the value of the position of the element before the deformation, plus a value induced by deformation, you can eventually write the following. You have Q0 ij transposed times MFF times Q0 plus so basically what I'm saying is that you have, if you expand your QE as a constant term, and then the one expressed by deformation, you get 3 terms here eventually because you sum the two. So this is what? This is the moment of inertia of the body when it is undeformed, and it's constant. While these are 2 contributions due to the fact that the body, the element in this case, is deforming. So conceptually, what I'm saying is that as long as the element deforms, it also changes its moment of inertia about the rotation, because it changes its shape. Okay, and you can see it here. Okay, so this is constant in time, and it's the initial one. And then you have this second term, which is the one due to deformation, because the element is changing its shape. The last one, and then we're done, is M ij theta f. This is the integral over Vij of rho ij applied over R applied over I with a tilde. This is again the matrix 0, can't remember, yeah, 1 minus 1 and 0. And N ij in the V A. And this simply, again here, remember that R ij is N ij times Q E. This is typical. And so we can write it as QE ij transposed applied over the last shape, inertia shaped integral. So it's SPCF with a tilde if you want, where this constant quantity C1 ij transposed applied over ij transposed. Then you have this I tilde, and then you have psi. So it's kind of similar to what we have already seen, but not quite the same. Okay. So this is basically, we have seen before this, instead of this with a tilde, we have seen this, which didn't have this part inside. Okay, but the rest is the same. But again, this is a constant term. So, certo che è trasposto. Okay. So this is basically close all the part of the mass. Tomorrow we will, in the very first part of the lecture, we will see the stiffness matrix, which is going to be much shorter. and then we will start the last chapter, okay, which is kind of short. So we're going to only have two main subjects, Gaia and iron condensation, and then the dynamic condensation. Okay, and then we will close the course. So still, we'll probably need all of the lecture, the 3 remaining lecture next week. Okay, just not to be in a hurry. Last thing that I wanted to mention: tomorrow we're gonna have 4 colleagues of mine, so 4 professors that will assist. They will attend the lecture as students, if you want, because there is a process ongoing of enhancing the quality of the teaching. Okay, so it's a university program, so it's not just for engineering, so not just for the faculty, but it's for all Sapienza. And in this frame, they will assist and they will write down, I don't know, a summary of a report with all their impressions. So it would be nice if you could assist in person, okay? If you cannot, it's fine, but it would be nice because, you know, you can also ask questions and so on, okay? That's it. So we stop the recording.